In this video, we will see 4 examples of solving homogeneous second-order linear equations with constant coefficients by using the characteristic equations. Example 1. Recall that to get the characteristic equations, we need to change the derivatives into the corresponding powers. So for this example, you can tell here the second-order derivative turns out to be a second-degree power, and the first order, first degree, zeroth order, zeroth degree, right? So we're going to copy the coefficients. And then we'll end with the quadratic equation, which can be solved by using the quadratic formula. So here I just plug the coefficients into the corresponding places. Now we simplify the expression, and we're going to end with a negative radicand here. And we understand the square root of a negative number is going to be imaginary, so that we get complex roots. So we understand in this case, the fundamental solutions are going to be products of exponential functions and trig functions. In particular, if we have complex roots as lambda plus mu I, then we know the real part, lambda, is going to contribute to the exponential factor. And the imaginary part, mu, is going to contribute to the trig parts. So for this case, you just need to put the negative half into the exponents. And the 1 here is going to be the coefficient for your sine and cosine t. So that's our fundamental solution set. And the general solution is going to be always a linear combination of the fundamental solutions. Okay, now because this problem is an initial value problem, so we need to apply the conditions here to determine the coefficients C1 and C2. So in order to apply the conditions, we need to first of all find the derivative of this general solution. So we're going to copy this, and then we can do the derivative here. In particular here, we understand because the two fundamental solutions, they are products, so that we have to use the products rule. Moreover, for the exponential factor, the exponent here is a function of t, so we have to use the chain rule, right? So you say the derivative of the exponential function is going to be itself, and then you take the derivative of the exponent, you're going to get a negative 1/2, right? So you're going to get the negative half here and here. You understand the negative sign is coming from the derivative of the cosine, right? That's the negative sign, right? Yeah. So that will be the derivative. And now we're ready to apply the two initial conditions. We understand the y of 0 is equal to 1. This one means when your argument t is 0, your y is going to be 1. So you just replace the t's by zeros and the y by 1, you can get one equation. And the second condition, the y prime of 0 is equal to -1 means when p is 0, so you can say we replace all the t's by zeros, the y prime is going to be -1. So we end with these two equations. And we understand that e to the zeros is going to be 1, cosine 0 is going to be 1, and the sine 0 is going to be 0, right? So we just replace those numbers by the corresponding values. And you can say here for the first equation, for example, because you have a 0 factor here, so the C2 term is gone. And we have just the C1 times 1 times another 1, right? So this 2 is going to be still 1 is equal to 1. And for the second equation, you can say in the parentheses, you're going to say the two numbers turns out to be just a -1/2 and 0. And for this one, you're going to say 0 and 1, right? So the two equations can be simplified into this way. And easily you can say the C1 is already 1, right? and we plug the value into the second equation, and you can get the C2 is going to be -1/2. So finally, we can plug the C1 and the C2 into the general solution, and then we can get the particular solution for the initial value problem. Example 2. Again, we have an initial value problem, but this time the initial values, the conditions are given at pi/3. It's no longer at 0. So we're going to see how to handle this case. Well, first of all, let's solve this equation. Once again, we're going to get the characteristics from the differential equation by changing the derivatives into the corresponding powers. Okay, to keep the coefficients the same, right? Yeah. And then for this quadratic equation, we can use a quadratic formula, and we simplify. We will get, again, a negative radicand, which will be imaginary, so that after you simplify it, you're going to get some complex roots for the characteristic. So now we understand the real parts and the imaginary parts are going to be included in the exponential factor and the trig factor of your fundamental solutions, right? So we're going to get the two fundamental solutions are going to be e to the real part 1/2 times t, and then cosine of the imaginary part times t, right? Another one is the e to the real part times t, and the sine of the imaginary part times t. And therefore, we know the general solution is going to be just a linear combination of these two. Okay, now we need to apply the initial conditions to find the C1 and the C2. So once again, we need to find the derivative of the general solution so that we can apply the second initial condition. So we copy the general solution and we start to do the derivative. So once again, because here you have a product of exponential function and the trig function, so we have to do the product rule, right? On the other hand, you know, for the exponential and the trig, you're going to say the arguments are also functions of the t, right? Of the independent variable t. So we have to also use the chain rule. So therefore, we'll say, for example, for the first term, when you do the derivative of the first factor, you're going to say the exponential function's derivative is going to be itself, and then the exponent's derivative is going to give you 1/2, right? Okay, and then times the second factor, right? And then you're going to use the first factor, the e to the t/2, times the derivative of the second one. We know the derivative of cosine is going to be negative sine. And then you have to do the derivative of the argument, which is a function of the variable t, right? So you're going to get another 1/2, okay? For the second term, you're going to say something similar, right? Okay, for these two parts, we notice that we have some common factors, 1/2 of e to the t/2, right? So we can factor that out of the two parentheses. And now we can apply the two initial conditions. So once again, the first condition means when my independent variable t is pi/3, my y value is going to be 0. So you can see here, I just replace the t by pi/3. So you're going to say 1/2 of them will be pi/6, right? And then my y value is going to be 0. Okay. The second condition is similar, right? So you're going to say y prime of pi/3 is equal to 1. That means when t is pi/3, my y prime is going to be 1. So I just replace the t values by pi/3. So that's why you say all of the t/2, okay, they become pi/6. And then I'm going to get the value is going to be 1. And now we can just evaluate the sine of pi/6 and cosine of pi/6. And we'll get the equation is going to be written in this way. Here we do not know the exact value of e to the pi over 6. So that's why we just keep them here, right? Yeah. Okay, now for this simplified equation system, we can simplify them further. For example, for the first equation, we notice that there's a common factor of half of e to the pi over 6. Half of e to the pi over 6, right? Yeah. And we can just divide both sides by this number, okay? And then you're going to say square root of 3 c1 plus c2 is equal to 0, right? Okay, so this is one thing. For the second equation, we can say we have a common factor 1/2 of e to the pi over 6, right? On the left-hand side. Moreover, we have another 1/2 from the two parentheses. So the common factor for both terms is going to be 1/4 of e to the pi over 6. Okay, so we can just divide both sides by 1/4 of e to the pi over 6, which is going to be multiplied by 4 times of e to the negative pi over 6. Okay, so if we multiply both sides by 4 times of e to the negative pi over 6, then we can eliminate this part and also the denominators here. Okay, so that we're going to end with two equations in this way. Okay, it looks much easier, right? Okay, so for this kind of system, well, you can just use, like, for example, in the first example, we just did the substitution, right? Because it's pretty straightforward. And for this one, you can do the same thing. You can also use elimination, or you can use matrices, okay? And for example, if I want to use the last option, I want to use matrix theory, and then I can write this equation system as matrix, the coefficient matrix, times the load vector C1, C2. And then I got my 0 and 4 times of e to the negative pi over 6. That's my load vector. Therefore, we know the unknown vector C1, C2 can be obtained from the inverse of the coefficient matrix times the load vector, right? Okay, so now the question is, how do we find the inverse of this matrix? Well, recall that if you have a matrix A, B, C, D like this, its inverse is going to be 1 over AD minus BC. And then you're going to just switch the A and the D here. And also you're going to put the opposite of the B and C. Okay, so that will be the inverse of the original matrix. Okay, so in this case, you can see here, we just use the exact formula and plug the numbers into the right places. Okay, so then we can say the inverse of this coefficient matrix can be obtained. In particular, if you check the coefficient here, you're going to say this is going to be 1 over, you got square root of 3 plus square root of 3 times of square root of 3 is going to be 3, right? And then you got a minus a square root of 3. So this first square root of 3 will cancel this square root of 3, right? Okay. And then you're going to get minus minus is plus 1, right? So you're going to get the 3 plus 1. That will be a 4. Okay. So you're going to get 1 over 4. So the coefficient here is pretty neat. Okay. And finally, you can just carry out the multiplication of this inverse matrix and the load vector, and then you can end with the solutions. Okay. So these are the C1 and the C2. Finally, we can just plug the two numbers into the general solution, and we can get the particular solution to the initial value problem. Example 3. Well, here we got, again, a second order problem, and we try to get this characteristic by using the same kind of property, right? We change the derivatives into powers of the corresponding order, right? The order becomes a degree, right? Yeah, you keep the same coefficients. For this one, actually, we can factor this quadratic polynomial, and we can get 3r plus 2 squared, right? So this equation becomes, well, we have 3r plus 2 squared is equal to 0, so that we know the two roots are going to be both negative 2/3. Well, in case you have difficulty to factor this polynomial, you can still use the quadratic formula, and you will end with the same roots. Okay, now we have repeated roots for the characteristic equation. And we understand in this case, the first fundamental solution is going to be just e to the rt, right? So in this case, negative 3/2/3t, right? And the second fundamental solution, we understand we have to give a multiple of extra t to the first fundamental solution. Okay, so you're going to get extra t over here. Therefore, the general solution is going to be just the linear combination of these two, just as you were, right? Okay, now, once again, because this is a initial value problem, we have to apply the initial conditions. And in order to use the second condition, we have to find its derivative. Okay, so for the first term, we just need to apply the chain rule, right? And you can say the derivative for the exponential function is going to be itself. And the derivative for the exponent is going to give you a negative 2/3, right? For the second term, because this is a product of a polynomial and the exponential function, we have to do the product rule, okay? So you can say the first factor's derivative is going to be 1 and 1 times the second factor, right? That's it. And for the second factor's derivative, we know that the derivative of the exponential function is still exponential, right? And the derivative for the exponent is going to give you a negative 2/3. So that will be the derivative for the second term. And here we can simplify this second part a little bit by factoring the common factor e to the negative 2t/3 out. Okay, so that will be the y prime. Okay, now we're ready to apply the two conditions. So once again, the first condition simply means when my input t is 0, my output for the y is going to be negative 2, right? So you replace the t's by zeros, okay? And then you're going to say the value is going to be negative 2. And the second condition means when my input t is 0, my derivative is going to be 1. So you just replace the t's by 0, and you're going to say the expression is going to be equal to 1, right? The derivative is equal to 1. Okay, now, once again, we have e to the zeros is 1, right? So you use this fact, and the 0 times whatever is going to be just 0, right? So you will say the equation system can now be simplified, and easily you can say the first equation actually is going to be just the C1 is equal to negative 2, right? Because C2 has coefficient 0. And then you can plug the C1 is equal to negative 2 into the second equation. So you can say negative 2 times this will give you positive 4/3 plus C2 times 1 is going to be 1. That means your C2 is going to be negative 1/3, right? So finally, we just plug the C1, C2 into the general solution. We can get the particular solution to the initial value problem. Okay, example 4. Well, this one is similar to example 2 because the initial condition is going to be given at 2, not 0, right? Well, let's say, how do we deal with this case? Well, first of all, we got the characteristic of the differential equation. And once again, you change the derivatives into the corresponding powers, right? Well, for this quadratic equation, you can solve this by factoring the polynomial. It's actually 2r minus 5 squared, so that you can get your r1, r2. The two roots are going to be 5/2. Once again, if you want to use a quadratic formula, it's definitely possible, okay? And you'll get the same roots. And for repeated roots, we understand the first fundamental solution is just coming from the standard formula, e to the rt, right? And the second fundamental solution is coming from actual t times y1, right? So we know the general solution is going to be the linear combination of them. And once again, for an initial value problem, we need to apply the initial conditions to find the C1 and the C2, and to apply the derivative condition, we have to find the derivative, right? So we copy the general solution here, and we try to find the derivative of it. So once again, the first term, we just need to use the chain rule, right? Exponential function's derivative is going to be itself, and then you have to do the derivative for the exponent. That will give you 5/2. For the second term, it's a product, so we have to use a product rule. And once again, the derivative for t is 1 times the second factor, right? And the derivative for the second one, you have to use the chain rule again, right? We already got the chain rule here, right? Yeah, and then times the first. So for this second part, we can factor the e to the 5t/2, and we can get the y prime. Okay, now we can apply the two initial conditions. So this time, once again, they are given at t is equal to 2. So we just need to replace the t values by 2, right? Yeah, in particular for the first one, when t is 2, y is 1. So you can say here, when we replace t by 2's, so the 2 will cancel the half, right? Yeah, so you're going to get c1 e to the 5th plus c2, and you get 2 times e to the 5th is equal to 1, right? And for the y prime, you get the similar situation, right? Plus you can plug the 2 into the places of t, and then you're going to say the equations can be written in this way. Okay, so now we can just divide both sides by e to the 5th, so that we can get easier coefficients to play with, right? So we just divide both sides by e to the 5th. Okay, and now you can say, for the second equation, we also multiplied by 2, okay, so that we don't have to play with fractions, okay, so that you get 5. And here you have 6 times 2 is going to be 12, right? And the other side, you're going to get 2, right? Okay. Now, for this equation system, once again, you can use either substitution, elimination, or matrix theory, right? Yeah. So for this one, for example, if we try to do elimination, in particular, if I multiply the first equation by 6, then I can get 12c2 and 12c2. These two parts can get canceled, right? Okay. And for your c1, you can say 6 times of c1 minus 5 times of c1 will give you 1 c1, right? And for the other side, you're going to say 6 times of e to the negative 5th minus 2 times of e to the negative 5th. That will give us 4 times of e to the negative 5th, right? So you can say your c1 can be easily obtained from the first equation times 6 minus the second equation. Okay, once again, 6 times of c1 minus 5 times of c1 is 1 times of c1, right? And 6 times 2 is going to be 12 times of c2 minus 12 times of c2 canceled. And 6 times of e to the negative 5th minus twice of e to the negative 5th you get 4 times of e to the negative fifths, right? Okay. Now, if you plug this into any of these two equations, for example, the first one, you're going to say, I'm going to get 4 times of e to the negative fifths plus twice of C2 is equal to e to the negative fifths, right? So we just move the 4 times of e to the negative fifths to the other side. I can get twice of C2 is equal to negative 3 times of e to the negative fifths, right? Divide both sides by the coefficient 2. We can get C2 is going to be negative 3 over 2 e to the negative fifths. Finally, we just plug the C1, C2 into the general solution. We can get the particular solution to the initial value problem. Okay, so in this video, we checked out the other two cases for second order problems, right? So here we know if we use the formula, use the patterns to get a general solution is pretty straightforward. So essentially, you just need to solve some quadratic equations, right? Yeah. So if there's any difficulty, the difficulty will be if we have some initial conditions to apply, then you have to, carry out the corresponding derivatives and solve the corresponding equation systems. Okay, thank you for watching.